Hi, this is Chrisferb, and I'm going to review an introduction to hypothesis testing. Okay, so up to this point in a typical statistics class, you have reviewed and studied the ideas behind central limit theorem and standard deviation and probability. And this hypothesis testing is all based on essentially the probability of what we would expect and what we know is to be normal or is said to be normal. So with hypothesis testing, just like many people learned in elementary school, is we make a hypothesis, we do a test, and then we say if we reject or do not reject the hypothesis. In elementary school, it's probably done a little bit simpler, which is where you say that something ended up being true or not true. So in this case, what we do is we don't confirm something is true as much as we reject that it is true or not, I guess. And I'll explain it more. But what we do is we either fail to reject or we reject. And if you think about it, it's very backwards in a negative way when we say we fail to reject. What that's saying is you kind of accept, but we're not saying what it is as much as we're pretty sure what it isn't. And that's an important point in the way that it's all phrased, because we're not confirming as much as we are confirming something is not like something else. Okay. So the first part of this, when I go through these notes, I try to make it as generic as possible before we get into the more specific. And so in the first part, I talk about how these are generic notes in that we use hypothesis testing with Z distribution, T distribution. We'll later use it with ANOVAs. We'll use, which is an F distribution, and then we will keep going on with that. So you can use hypothesis testing for all kinds of things, and that's because, as I mentioned at the start of this, hypothesis testing is made to test the kind of the probability of something being drastically different than what we would expect it to be. And that's the nuts and bolts of the way this works. In statistical hypothesis testing, there will always be two hypotheses. So the hypothesis B testing is called the null hypothesis. So the null hypothesis is, and it's given the symbol H0. So the null hypothesis is, if you think about it, the null hypothesis is status quo. So the null hypothesis is saying this is what we believe to be true as of this test. So it's always H0. And the reason why it's H0, I believe, well, if you look at math now, a lot of the way science and math, they're very, of course, interrelated. But with arrays and programming, we start at 0. And it's kind of funny that the null hypothesis is 0. It's not like 1. The alternative hypothesis is 1. So that's just the way it's set up. So the null hypothesis is 0. I guess the null would fit, but it's the first one. So it is the baseline. It is what we expect the status quo is. So remember, null hypothesis is status quo. Nothing has changed is kind of what we are testing for. So the null hypothesis states that there is no difference between the hypothesized population mean and a sample mean. It is the status quo. So that is the basics of that. We test the null hypothesis against an alternative hypothesis, also known as the alternate hypothesis, which is given the symbol HA or H1. I'm not sure which one's more proper, but you'll see them in textbooks. They fluctuate between HA and H1. If we're going with a number scheme, then H1, I guess, would be more appropriate. HA for alternative or alternate. The alternative hypothesis can be supported only by rejecting the null hypothesis. So this is what I was talking about before. We don't confirm the alternative hypothesis. We support the alternative hypothesis by rejecting the null hypothesis. So when we say we reject the null hypothesis, we're saying something is different enough to be concerned that maybe what we thought before was not true. So we, like I said, we do not accept the alternative hypothesis. We reject the null hypothesis. We're always making a statement based on the null. We never make a statement based on the alternative hypothesis. Okay, so we're always testing some idea against the null hypothesis, and that's just the way this is always set up. And like I said, we're not confirming that the alternative hypothesis is way different. We're confirming that there's something wrong with the null hypothesis. So it's a very subtle way of saying it, and we'll go into this more. Basic hypothesis example. It says a container of peaches being sealed should have 16 ounces of peaches. A quality assurance specialist believes the containers are so they weigh more than 60 ounces. They believe they're greater than 60 ounces. The null and alternative hypotheses are, so it says this is our null hypothesis, H0, and this is mu, this is our population mean. And so we say that and this is saying what we believe to be true right now, that mu is less than or equal to 16 ounces, and the alternative hypothesis is mu is greater than 16 ounces. So we always set these up like this, as long as we're not doing a two-tailed type of distribution test, a two-tailed test, we always set these up with the null hypothesis being equal to or less than or greater to. So that's the standard. And then the alternative hypothesis is always going to be based on what we're testing for. In this case, we're doubting that the containers actually weigh 16 ounces. We're thinking that they weigh greater than 60 ounces. So that's why the alternative hypothesis, the statement of the alternative hypothesis is where your action is that you're thinking about. Like I said, we don't confirm the alternative. We reject or do not reject the null. And so in this case, we have mu is greater than 60 ounces, and that's what we're thinking that. Okay, so then it says the null hypothesis states that the population has a mean equal to 16 ounces. Our alternative hypothesis states that the population has a mean that is greater than 16 ounces. So of course this is a very simplistic example. Okay, so it says a more realistic example of a standard normal distribution hypothesis test. A population of adult males has a mean weight of 180 pounds with a standard deviation of 20 pounds. A researcher wants to know if the mean weight of males in a particular area is different from the population mean. So that's kind of what we're testing for. We're testing to see if something is different than what we thought it was. A random sample of 35 males provided a sample mean of 188 pounds. Perform a hypothesis test to determine if this is evidence of a significant difference for the mean weight of adult males in this area. And it says, now let's write our hypothesis statement and label the parts. Okay. So what we do is we write out our null hypothesis, and our null hypothesis says that they weigh 180 pounds. Now, you say, okay, it says that they weigh 180 pounds. So what's up with this or less than? So they weigh 180 pounds. And so we know that this is our null, but until we look at the rest of the question, we don't know if this is going to be mu is less than or equal to, or how that's going to lay out. So when we look at the statement here that we're testing to determine if there's a significant difference, and the assumption is that they are heavier, then we're going to go and say that the test, our null hypothesis, is that they are equal to or less than. Okay, I'm going to pause this real quick. Okay, back. Okay, so our, as I stated, the alternative hypothesis is the assumption that it's greater. And, you know, to tell you the truth, most of these questions, this says significant difference. Most of these questions are a little bit clearer than this example. They'll say greater than, and that's kind of a common setup that I do. And usually there's no assumptions here. I mean, obviously this one's greater. Okay, so what we do is I always write out in my questions early on, because it's going to, whether we use the t-test, t-distribution, or the normal distribution, it all comes down to taking a look at the data that we have. So this says sigma is known and n is greater than 30. So this is kind of a bulletproof example that we're going to use the standard normal z distribution. Okay, it says you should always write out your figures in hypothesis statement even if you will solve it with the calculator. So I really recommend that you, number one, you don't go straight to the calculator, because you can come up with the wrong answer in your calculator right off the bat and not know that you're getting the wrong answer. So what you want to do is write this out. Now, I'm sure there's people, I've seen these people from talking with people in education, where they say that usually it's kind of people who think that they're high and mighty, but they think that you shouldn't be teaching people how to do some of these things by hand. Well, you need to learn how to do this by hand before you rely on the tools. And whether you are going to be doing this by hand all the time, I recommend you don't, but you need to learn how to do it by hand before you appreciate and understand the inputs going into the tools, such as the calculator. So always write this out, especially for an introduction to statistics class. I'm going to show you the steps. You write it out, you draw the picture, you do the whole thing before you go and check it on the calculator. Okay. So in this case, we know that we're using the standard normal z distribution. And so we have mu, and we're writing out what we know. So mu is 180, and then the standard deviation is 20. Then the x bar is, which is the sample mean that we're testing for, is 188 pounds in this case, but it's 188. Our n is 35, so we have a decent sized sample. So, so that's kind of the initial setup of this. And now look at, let's look at another one of these. So this is, it says more realistic, and I mean more realistic because the t-test is a little bit more forgiving and a little bit more realistic because we don't always have the population standard deviation. And it's more forgiving, but technically the standard normal distribution could be a little bit more accurate. Remember, the t-distribution has fatter tails. So it says a population of adult females has an average weight of 140 pounds per the National Institute of Health. A firm wants to see if the average weight is correct, so they weighed 25 females and found an average of 145 pounds with a standard deviation of 8 pounds. Perform a hypothesis test to determine if the National Institute of Health figures appear to be correct. So once again, this is modeled after the other one, but our assumption is that they weigh more. So it's the same setup. In this case, though, sigma is our population standard deviation is not known, and n is less than 30. So for sure, we're using our t-distribution. Now n is 25. It's not a big deal, but it is less than 30, and standard deviation is not known. Population standard deviation. So the other thing that I want to point out before we go too far, okay, So this is another thing that I do in my questions. It says a firm wants to see if the average weight is correct. So they weighed, when they say they weighed, they're doing a sample, 25 females, and found an average of. So now this is what they found. This is not the population. They found an average of 145 with a standard deviation of 8 pounds. So this is a sample standard deviation right here. Okay. So I usually when I do these questions, I'll put the usually population data first, sample data second, and when I have a sentence and I say that there is a sample mean, and then I say and a standard deviation of this, what I mean is that that's the sample standard deviation. So as we go through these hypothesis tests examples, I'm going to point this out more and more because we have to be able to pull the parts out of the questions. Okay, so then I list out what we have, and what I have is the population standard deviation, big S for the sample standard deviation, X bar 145, that's the sample mean, and then N is 25. This is a sample standard deviation. Do not mistake for the population standard deviation. The sample standard deviation is stated with the sample mean. That's exactly what I was talking about. Okay, so now we're going back into. We're going to be looking at decision process and how the distribution, and we're going to go into rejection zones and things like that. So the foundation of hypothesis testing. We had introduced the central limit theorem, in prior videos. This states that if we take a random sample of any population data, then the mean sample has X bar has a distribution that is normal with a mean equal to the population mean, from which the sample is taken from mu. So what we're saying is, if we go and we take a sample from a normal distribution that is normal, then we will have a mean that's equal to the population mean. And essentially, if we took a bunch of means, we would have a very similar model of the population, mu population. And it says, and a standard deviation equal to the population standard deviation divided by the square root of the sample size. These are the theorems here that I'm talking about, which is in a prior video. One would expect that a sample mean obtained from a normalized population would have a normal distribution grouped around the center where the probabilities are the highest around the mean. So remember, in a distribution, when we see the high points of the distribution, that's the what that means is the data, when you shake it all out, the data is more frequent, meaning there's more observations of certain values in the middle part. And so those are more common. And it says the further, let's see, are the highest random. And if indeed the group population mean is 100 ounces, for example, then the chance of getting a sample mean of 100 ounces is much higher. So we have this population, and then we go and we know what the population mean is. We say it's 100, and then we go and we take a sample from that population, and we know that it should be somewhere around 100, depending upon the sample size and this up here, which we dealt with sampling distributions before. So, and of course, the sample size has to do with that. It says the further our sample mean is from the population mean, the more likely we are to reject the idea the population mean is what we thought. So if we go and we take a sample from the population, and we go, well, the population mean should be 50, whatever this is, and we do a sample that's significant, large enough, and all. I don't want to use the word significant, large enough for what type of tests we're doing in the whole thing, and we come back and we find out that the sample mean is 20, then we should be scratching our heads. Either we did a very poor sample and we had some real sample problems, or it's possible that the sample the population mean is not what we thought it was. Now here's another thing, slight deviation from what we want to be talking about. If we end up rejecting the null hypothesis, that doesn't mean that that's just the way it is. What it means is we should do more tests. And if we can verify through more testing that we come to the same conclusion, then that is really a strong indication that the population is not what we thought it was. One hypothesis test does not tell us the way the world actually is. It tells us it might be a clue into we need to do more testing. Okay. So this was saying if we do a sample from a population that we would expect it to be similar, and if it's not similar, then we need to consider rejecting the null hypothesis, depending upon what we call our significance level. Okay, that's the cutoff. So the probabilities gradually decrease in the tails, implying that as we move away in either direction, the probability of getting a sample mean in that area decreases. Okay, so really high probability in the middle, and as we move away, the probability decreases. And that's because if you look at the distribution, it points that out in the distribution because the tails get real thin. And remember, as we move further away, the actual number, the value of the data increases. Meaning, if we had accounts of things and they had a value on them, as we go out, that actually, as we go to the right, the number increases. And then as we go up, that's the frequency of that value number. So as we move out, it becomes less likely. And as we move up, that's the frequency of how many of those occurrences are. So what we're saying when we look out on this tail is that these are very rare events or observations of our data. So these are super rare, and that's the way this works. So let's see, the probability of getting a sample mean in the area decreases. They're talking about going into the tail. This fact is used to come up with this so-called rejection regions in the hypothesis test. And the logic is if the sample mean that we get from a sample falls in either of the rejection regions, then we conclude that the sample could not have come from a population data with a mean that equals, in this case, we're talking about 100 ounces in this example. The size of the rejection zone is determined by the significance level of the discussion below. So the idea is, as we move out further and further, we do this test and we say, we know the probability because of the central limit theorem of the probabilities of being out in the tail. And then we do this test and we say, oh, wow, our sample mean is way out in this tail area of the distribution. So we say we need to reject the null hypothesis, which said that the sample mean is in this area. What it means is the sample mean may actually be a little bit different depending upon our parameters. Okay. So type 1 and type 2 errors. So these are not easy to think about, and let's see. Let's do some explanations here. This is a table of error types, and we have the data goes two different ways. Okay, so on the horizontal plane, we have decision about null hypothesis. So we have fail to reject and reject. So fail to reject means we did not reject the null hypothesis, meaning we believe everything is true. Okay, we believe the null hypothesis is okay. We failed to reject it. This is where there's a little bit of double negative stuff, and this is the way they do this. And then reject means we actively rejected the null hypothesis, which is rejecting the status quo. Okay. And then we have these vertical two cells here that say true and false. So this says null hypothesis is, so this is, over here is our decision, and up here is reality. So reality is what the null hypothesis is, whether it's true or false. We have no bearing over the actuality of our null hypothesis. So we have true and we have false. So in this case, let's take a look at this. Let's say we said decision about null hypothesis. So we failed to reject it, which means the status quo appears to be valid, that our belief in the status quo appears to be valid. And then for the actuality of it, let's say it's true. So we fail to reject it, which means we believe it's true. And then in actuality, it is true. So it says correct inference. And that means true. It's a true positive. So the probability of this is 1 subtract alpha of getting into this. Now, if we go down below, let's say we rejected the null hypothesis, yet the null hypothesis is true. What we're saying is we threw out something. If you think about it, in your refrigerator, you throw something out, you wonder if it's bad, you throw it out, and then you find out it wasn't bad. So that was more of a type 1 error. That was a false positive, in that you thought it was bad, you rejected the null hypothesis, which was, oh, this thing's good, but you reject it, and then you find out that nope, it was actually good, and so that would be a false positive in thinking that it was bad. I understand these are complicated, and I have to use tables sometimes to really make sure. It's just tricky, and then it's written in kind of in like negating language. So then let's take a look at this column right here. So in this column we have the type 2 errors, and in this one it's a false negative. So we have false positive, false negative. Okay, so in this one we failed to reject the null hypothesis. We think it's good. We think it's true. We think the status quo is fine. And then in this case, the status quo is actually false. It is not that, and we should have rejected it. And so we thought that we thought it was good, but it was not good. So this is a false negative, and the probability of this is our beta value, which down below we'll go into that. And then down here on this next one, this is where we have the correct inference, and that is the true negative. So in this case, we reject the null hypothesis, and the null hypothesis is not true. So that's how this works right here. So the parts that are shaded, these are our errors. And so just to recap, we go back, a type 1 error is the false positive. So that is, oh, we're checking to see if something in the refrigerator is bad. Oh, it looks like it's rotten, and we think it's rotten, and we reject it, but it is not rotten. So that would be, we reject the null hypothesis, we think the food is bad, and we throw it out, and it was actually good. So that was true, that the food was actually good, but we threw it out. For the type 2 error, we have the, let's see, we failed to reject. So we're looking at our food in the refrigerator, and we don't throw it out. So we failed to reject, and the food is actually bad. So if you can think about this, we get sick from our bad food, so that's not good. But we think it's good. So there's kind of two sides of the coin here. And then take a look at this. The probability is the beta for this one. The probability for this one is alpha. So depending upon what we're testing, the consequences of being wrong could be really important, whether we're wrong or not. Now, if the test isn't sensitive enough, then we will have these errors as well. So if you look at this, we have alpha and beta. So these are both the inverses of each other. And we'll talk about this more too, and I'll probably go back to this. A courtroom example of type 1 and type 2 errors. A type 1 error occurs when convicting an innocent person. So a type 1 error right here. Okay. So applied to hypothesis testing, the probability of this occurring would be the value of alpha. Okay. And then type 2 error. A type 2 error occurs when not convicting a guilty person. So this is kind of like the refrigerator example. We don't convict our food here. We don't throw it out, but it's actually bad. And the other one is that we reject. We threw something out, but it was actually good. So you see, talking about putting somebody in jail, corrections, convicting somebody. Type 1 and type 2 errors are really important on the way that works. So it's a huge issue. In regards to the standard normal distribution, the relationship between both A and B are shown below. As you can see from the graphic, alpha decreases, beta increases. So when one gets larger, the other gets smaller. And of course, this whole distribution, we only have the number 1. We only have 100% to work with, so we can't make up space without cutting into the other space. When testing for hypothesis significance, the alpha value is used as the level at which one is willing to accept the test value as significant when it is the result of a mere consequences. This is really important. I should actually highlight this more in my future notes. I'm going to repeat this. When testing for hypothesis significance, the alpha value is used as the level at which one is willing to accept the test value is significant when it is the result of a mere consequence. So what this means is our alpha level, and typically, let's go back to a term that we've used before. We're talking about confidence intervals before. Well, I just want to explain when we think about, say, 95% confidence interval, which we've talked about in some other ones. So if we think that beta in this case is, say, 95%, then the alpha is 5%. And so let's say this alpha is 5%. And so what that means is we're willing to be wrong 1/20% of the time. We're willing to have a type 1 error 1/20% of the time with having the beta portion be 95% and the alpha be 5. And that's the nuts and bolts on what we do with this. So we do a test and we say, well, the probability of the mean falling within this range is it's really rare. And if it's in this area, then we're like, well, either we're wrong by mere chance, or that the actual sample mean is different, which means the population mean is not what we thought. So this is the whole way this works: is we're testing against the population, and we're willing to accept that 5% of the time we're just wrong because we're wrong. 95% of the time we're going to be correct when we reject the null hypothesis. And so that's why often we end up with this 5% alpha value and 95% the beta value. Okay, let's take a look at how this works. But this is very important when it says, so this alpha value is the willingness that we will be wrong that percentage of the time. And we're betting that we're only going to be wrong 5% of the time, and with the beta we're going to be correct the other part of the time. Okay, rejection zone method. Now historically they used rejection zone method because doing the actual calculations is easier. And so here we go. There's an internal research hypothesis of which the truth is unknown. The first step is to state the null and alternative hypothesis and draw a picture showing the rejection area. Okay, so we draw the picture, and then we want to show the rejection areas and things like that. But first we draw the picture. And then what we do is we have the, depending upon the way that the wording is, we if we see greater than, more than, then we end up usually with the right rejection area. It's usually in this tail right here. So the question says the normal state of affairs is this, and we think that the true state is actually greater than that. And so we end up with our null hypothesis, which is less than or equal to, and our alternative hypothesis, which, like I said before, it could be HA or H1, is greater than. And so that tells us we're in this right part. And then the other one is when we see the less than or up to, you'll see. And in that case, usually they're written with a null hypothesis being greater than or equal to, and the alternative being less than. And then the last one is when we see the term different. And this is where I'll probably go back and change one of the prior kind of introductory notes. But usually when you see different, it is something is not what we thought it was, and it could be high or low. And usually in my questions, the way I do is I say that they believe it could be high or low or something. I give you this range of it could be, it's whatever it is, it's not what they thought it was. And this is left and right rejection areas. Now the alternative hypothesis, now here's one other thing here. The alternative hypothesis in this case is a not equal to, and that's what we're checking for, not equal to. So one thing to point out here is that the alternative hypothesis never has the equal sign. It's either not equal or it's an inequality, but there should not be an equal sign in the alternative hypothesis ever. Okay, so we choose the appropriate test. We draw the diagram of the distribution and identify the rejection zone by shading the proper region as described in step 2. So we figure out where this is, and we're going to just shade that. We don't have to pick how far into the distribution the line is. We just pick a spot that has that tail part that divides it. It says draw a diagram. Okay, select the significance level, which is alpha, probability threshold below which the null hypothesis will be rejected. Common values are 5% or 1%. When performing a two-tail test, one must divide the significance level, the alpha, by 2. And so when we do a two-tail test with the z-score, we usually take that 5% and divide it in half. And so when we do that, it makes it so that the z-score changes. So if the z-score before was 1.65, the z-score becomes in each tail 1.96. And we'll go into this more. Probably more in some of my other videos. I have other videos on this, so I really recommend you take a look at that. The distribution of the critical value statistic under the null hypothesis partitions the possible values of the test probability into those for which the null hypothesis is rejected, the so-called rejection region, and those for which it is not. Okay, so this is called the rejection region. I call it the rejection zone typically. And what that means is we do the calculation, and our figure that we calculate ends up being in the rejection zone. So this is, if it's in the rejection zone, what do we do in the rejection zone? We reject. And so that's kind of easy. That's the way that we remember it. And we shade this just so that we know where the rejection zone is. So if our calculated value gets into the rejection zone after we look at the table and we get that value, then we reject it. So yeah, we calculate the test statistic, and then we're going to see if it gets in the rejection zone. The decision rule is to reject the null hypothesis H0 if the observed calculated statistic value is in the rejection region, the rejection zone. Do not reject the null hypothesis otherwise. So if it's not in the rejection zone, we do not reject. If it is in the rejection zone, we reject. Then we write out the hypothesis statement similar to, this is a generic one, since the sample mean of whatever is or is not significantly more, less, or different than the population mean of whatever it is, we must reject or not reject the null hypothesis. Thus, then we write out what the conclusion means. For example, graduates are earning more than expected. Okay. So this is really important here. This is something to remember. So as we move further away from right here, the mean, population mean type of thing, or any type with a normal distribution, anytime we move away from that super frequent spot of the observations of the data, in this case it's symmetrical, so it's in the middle, the probability of finding observations of the mean once you calculate it out from a sample decreases. So as we move further out, it decreases. So in this case, z-scores and t-scores will decrease as we move further away from the mean of a sample, of a population. And because we take samples from the populations, then we draw the conclusions. So it's all based on, essentially the idea that as we move further away, the probability decreases. Now, the z-scores and t-scores increase because the t-scores and z-scores represent standard deviation, kind of a normalized standard deviation. And so as we move further out, the z-scores and t-scores increase. And that's just the way it works. So they increase as we go out. Okay. And then if we've laid out our critical value, we know where that is. And then if the z-score or t-score passes that critical value and is higher, then it's in the rejection zone, and we reject. Now, for the p-value process, some people may think it's easier or not easier. There are some advantages to it. Now, in the past, doing the actual p-value calculation was hard to do, but now calculators are a lot better at it. When we do the p-value, you do this on your calculator, TA83 or 84 calculator, you'll see that doing the t-score calculations where it produces a p-value, it actually takes your calculator more time. It's not as easy for your calculator. So this is why in the past everything was done with rejection zones. It's much easier to work with rejection zones than the p-values for your in the past, before calculators made it really easy. So it says follow steps 1 through 5. So 1 through 5 are essentially the same. We select where everything's going to be, and then we get to the point where it says compute the observations, the observed value from the test statistic. So we're doing the calculation of the test statistic, and we calculate the p-value. This is the probability under the null hypothesis of a sampling test statistic, at least as extreme as that which was observed. Okay, so let me show you the picture real quick, and then we'll go back. So p-values end up, now these are probability values. So as we move further out, the probability decreases. The only real difference in this and the rejection zone with the t-scores and the z-scores are that they both are doing the same thing. It's just that, think about it, as probability decreases and the actual number gets smaller, the probability decreases, the number gets smaller. With z-scores and the calculated scores, like the t-score, as the probability gets further out, the t-score actually increases. So they're flip-flop. They're both doing the same exact thing. It's just that as we move further out, the actual probability, the p-value scores decrease. Where before with the rejection zone method, they actually increase. So we do the same thing, but it's just flipped. Okay, so that says calculate the p-value. Okay, test significance level alpha, where, let's see, if the significance level of alpha, say 0.05, and then if it's greater than the calculated p-value, we reject the null hypothesis. So what that means is, let's say the test significance level is 0.05, and it is greater than our calculated p-value, which we'll say is 0.02. What that means is our p-value, our calculated p-value, is actually in the rejection zone area, and we're going to reject it. So it says reject null hypothesis. If the test significance level of alpha, let's say it's 0.05, same thing, and the calculated is actually larger than our test significant level, it means it's not in the rejection zone, and we do not reject the null hypothesis. So write the hypothesis statement similar to, and it's the same type of statement that we're going to do. This will be a long video, so I'm probably going to take a break in just a sec, and I'll pause it and come back. So this picture, it is super important, but just the big thing here is the p-values increase as we move away. And the other one, the z and the t-scores increase. So this one, they decrease, meaning probability is less common event occurring. There's the probability of the event occurring decreases, and that number is represented in the probability, the p-score, where this one, the probability is in standard deviations away from the mean. So as those numbers increase, they become less probable. When we reject the null hypothesis, it means our test findings are significant enough based on our present level of significance alpha value, and have accepted the risk of mere consequence appearing as the true diversion from the status quo. So what that means is, if we reject the null hypothesis, we're accepting that there is a little bit of a risk that we're wrong, but that risk is manageable enough, which is why we set up the significance level to that point. So that's where I always say you need to do another test. If this was real life and you're trying to figure out if a parachute's going to open, you don't just do pure random chance of a 1/20th chance, which is the 5% alpha usually. So you do another test, and you do a couple of tests, and you go, they keep coming up that we keep rejecting the null hypothesis, which means, well, the status quo is not what we thought it was. Okay. I'm going to take a break just real quick. I'll be back. Okay, I'm back. Okay, significance level. So we've already talked about a little bit of this. Scoot over. And the big deal was when they came up with this, it was the idea that what people are willing to accept being wrong. The amount of the time people are willing to accept being wrong. And this was by Fisher, came up with this in 1925 in his writing called Statistical Methods for Research Workers. So the interesting thing was he came up with this and he said, well, realistically, if we flip a coin, 20 times, what is the likelihood that we're going to be wrong if we're testing to see if the coin was accurate? And this idea of the 5% alpha, or the p-value being 5, kind of stuck. And so what happens is we end up with this 5%, and it has been prevalent for the last 100 years. And people debate. I've read scientific magazines, statistics magazines actually, and they debate this whole thing. And either way, it's still stayed. And some people in the scientific community say that it should actually be smaller depending upon what you're working with, and that may be the case. But that's what this is about. I'll post this information. So that's the deal. The 5% alpha came up a long time ago, and it was like, well, we're willing to be wrong about 5% of the time, and it's kind of stuck. This is a big thing, though, that I'm talking about in practicality, and that is, as I've mentioned before, if you reject the null hypothesis, you could be wrong. Let's say you do the first one and you reject it, you could be wrong. But if you do this over and over again and you retest, then your chances of being wrong decrease. And so what it tells you is that the actual, it adds significance and credibility to the tests when you reject them. If you have multiple times that you are rejecting the null hypothesis. Okay, your calculator. So on your calculator, like I said, I have some videos up of this. So I have more times where you can check this out. But on your calculator, you go and you click on the stats button, and from the edit menu, click the right arrow twice, and your screen should now look like this. Okay, so let's see. If you click your I was like, well, if you click it twice. So if you click it twice, it actually should look like, I should move this. It should actually look like this right here. When you click it twice, you go from the edit over to the tests. And you get the z-test and the t-test. And the z-test, as it appears to be, it is for the z distribution, for the standard normal distribution. And then the t's for the t distribution. Okay, the big things here to point out are, let's see, our mu is the same. Okay, so this one has the population standard deviation. This one has the sample standard deviation. SX means sample standard deviation. Let's see, one other thing. Other than that, most of it's the same. This is a big thing to focus on, this right here, where it has the mu and then you have these selections. So this one right here, on both of them, same thing. This is the inequality for mu must reflect the alternative hypothesis in both the z and the t-test. So if you go and you write this all out, you select whatever your alternative hypothesis looks like, and you select that one. It should actually match one of these things. And a little hint that it is the alternative hypothesis is that this is not equal to, and that will never be your null hypothesis, and these should not be your null hypothesis as well. So this is always your alternative hypothesis. Make it match, okay? And it'll give you the answer, and the calculator does a pretty good job with that. So it'll list the data, and like I said, I have more videos on this. If you're doing the t-test, I think both of them give you the p-values, and I think both of them give you some of the nuts and bolts values. Like I said, there's more videos, you should check it out. Okay, let's take a look at how these things work. The questions. The standard time it takes for an 8-year-old to swim 25 yards is 16.34 seconds with a standard deviation of 1 second. Chuck, the typical Uber parent, thinks that his son is better than other 8-year-olds, is sure his son Billy can swim 25 yards faster than average. To test his hypothesis, Billy swam 32 times and obtained a mean time of 16 seconds. Based on this research, can it be concluded Billy is a faster swimmer in the 25-yard distance than the typical 8-year-old? Use a 5% level of significance to test this hypothesis. Okay, so we list out what we know first, and a couple things here right off the bat. So we list this all out, But one thing to be aware of, it says the standard deviation, the population standard deviation sigma is known, and the sample is greater than 30. I usually try to actually have both of these be true or false. Just so it's kind of clear that it's a standard normal distribution. Okay, so we write out our null hypothesis, and our null hypothesis is that mu is greater than or equal to 16.34. And that is because it says the standard time it takes for an 8-year-old to swim 25 yards is 16.34. So it is the null hypothesis is that's what he equals, or greater in this case, because the alternative hypothesis is going to be he's faster, which means it takes less time. So the alternative hypothesis, the HA, is less than 16.34, and then mu is 16.34. Standard deviation is 1 second, and that is the population standard deviation because the 1 second standard deviation is with population data, because it says the standard time. That's population data. And then the X bar, to test this hypothesis, Billy swam 32 times and obtained a mean of 16. So they went out and they did their own test. So this is sample data. Mean of 16, swam 32 times. So we draw our picture. Always draw our picture. And we take a look at the direction of the alternative hypothesis inequality. It's pointing to the left. So I know that we are going to put a line right here, and our rejection zone is going to be in the left. Let's see. We also know that we are testing to a 5% level of significance. So our cutoff, we're going on this one, we're doing rejection zone style. So we're going to look up on our Z table, and we're going to figure out what our Z score is for the 5%. And let me pull that up real quick. Okay, so this is where we use our nice annotated things I made you, which say one tail or two tail hypo test. I'm going to zoom in. They're down here at the bottom. So we can do a couple things here. It's one tail because the alternative hypothesis is that he is faster, which means less than. One tail hypo test. Okay, we're going to find this one, but it needs to be with the 5% significance level. So this one's 1%, this one's 2.5, this one's 5%, one tail hypo. Okay. So on this one, we go and we're thinking, well, I need the Z-score is what I really need. So we go and we take this and we follow this up, and our Z-score is 1.65. So okay, that's the way this works. Now, if you're doing this without the annotated part, you'd have to figure out that one side is 0.5, and then the other side you would have to factor in the beta and the alpha, and you'd be looking on this whole table for the beta, and this is the beta, closest beta, this one or this one. And most people, I think, usually just end up with 1.65 versus 1.64. It's actually right in between. Okay. Let's go back to where we're looking at. Okay, so we got that, and we know now that our Z-score is 1.65. So we're good with 1.65. Okay, so we draw the line right there. 1.65 is our cutoff, and now we go and we want to get our calculated Z-score. So we have our calculated Z-score, and we're going to put in our data here. We have our x bar, we have our mu, and we have our population standard deviation, and it's over the n, which is 32. So put it all together, and we have 16 subtract 16.34 over 1 over the root of 32. And then we get the negative, we get the negative z-score of 1.923, and I'm going to zoom in just a little bit. It's 1.923, and it's negative. So negative tells us that we're on the left-hand side of the distribution. So that's what the negative means. It doesn't really mean much other than we're on the left of the median and the mean. Okay, and so this is 1.9, and this one is 1.65. So that tells us something here. So now we're going to go down. We're going to place our calculated value, and it's in the rejection zone right there. It's technically that you could say this one right here is negative 1.65. The negatives, like I said, don't really mean much, other than sometimes I'll leave the negatives on here to remind, like, it's on the left-hand side. So this is greater than this, so it's in the rejection zone. So it says, since the sample mean of 16 minutes is significantly less than 16.34, we must reject the null hypothesis. Billy appears to be able to swim 25 yards, the 25-yard event faster than the national average. Let's take a look at one more here, and then we'll do a couple more of these, and we'll probably start going a little bit faster. Let's see. Nationally, the starting average salary for a liberal arts degree graduate is $29,950, with a standard deviation of 750. However, a sample of 35 recent graduates determined the average starting salary of $30,250. This is probably some old example. Based on this research, what can be concluded concerning the starting salaries of graduates? Are they earning significantly more than expected? So more than is an important term we're looking for. And it says use 5% level of significance. And of course, it can be different. I use 5% a lot, but it could be different, and sometimes they are. Okay, so we write out the information that we know. It's all listed right here. Before I jump on that, it says the standard deviation is known and n is greater than 30, so we're going to use the standard normal z distribution. And let's see, our alternative hypothesis is that mu is less than or equal to 29,950, because this is population data. And the standard deviation is 750. But, and then the sample of 35 recent graduates determined the average starting salary of $30,250. So that is sample data. So we draw our picture, and the inequality always points towards the rejection zone of the alternative hypothesis. So this is where our line's going to be for our rejection zone. Now in this case, we did this last time, but what you would do is you would look up, if it was 5%, you would look up what the z-score is for 5%. And it's 1.65. And so this is our range, where once we're higher than 1.65, we reject. So we do the math here. And this is all, I mentioned how we go about these things with our sample distribution videos, sampling distributions. So we end up with a z of 2.366, and it's positive, which only means that we're on the right-hand side of this distribution, and it is greater than 1.65, so it's going to be in the rejection zone, which is right here. So it says since the sample mean of 30,250 is significantly more than 29,950, we must reject the null hypothesis. The graduates may be earning more than previously believed. Okay. Let's see. Okay, this is a t-test. Okay, this is good. So the t-test, so a couple things here. Number one, let's see, when we do look at the t-table, we are doing everything we can to get the t-score. So the tables are drastically different between the z-score, the z-table and the t-table, okay? And I'll point this out a little bit. Scientists in a lab think the thermostat is broken and the room is warmer than the thermostat shows. So right here, I'm giving you the greater than Q. The temperature is set at 70 degrees Fahrenheit. Since scientists like doing hypothesis testing, they took a sample of the temperature in the room for 17 days and obtained a sample mean of 73 degrees Fahrenheit with a standard deviation of 6 degrees Fahrenheit. Based on this research, is the thermostat broken? Perform a hypothesis test with a 5% level of significance. So in this one, they believe that in actuality it is warmer. So, write out the information. In this case, our population standard deviation is unknown, and n is less than 30. We're going to use the t-distribution. So our null hypothesis is the status quo, is the room is 70 degrees and or less. And then the alternative hypothesis is more than 70 degrees. Okay, and mu is 70 degrees. This right here, they talked about 17 days. They took a sample mean. So 17 is our n, and sample mean of 73 degrees, and the standard deviation, this is a sample standard deviation of 6. Okay. Okay, then it says draw the diagram. We drew the diagram and the inequality pointing towards the rejection zone. And this is the inequality of the alternative hypothesis, pointing towards the rejection zone right there. And so let's take a look. We're going to look at the t-table now. So it says t, so this is kind of how we can write this out so you can see what the parts are. So in this case, we're using 5% significance level and 16. So 16 is our degrees of freedom. And remember, I don't have it listed here, but your degrees of freedom in this case, in this stage of the game, it is in subtract 1. So it's always that way until I tell you otherwise. In subtract 1. So our degrees of freedom is 16. And then it's a one-tail test because we're looking for warmer. We know it might be broken, but everything points towards warmer. Okay? So that's how that's set up. So let's go and look at the t-table. And on the t-table, let's see, our degrees of freedom is 16. Okay, so we're somewhere in this here. Okay, 16, one-tail test, and 5%, I believe. 5%. And so it's this value right here. Okay. 5%, so one-tail test is 5%, and then 16. Okay. So 1.746. Okay, so we have that value there. So that whole t-table is set up just to get the t-score. And so it's quite a bit different than the z-distribution. Okay, so we get this value there. And then we do the calculated statistic. Okay, we put all of our data in. We get the calculated. It's a positive number. It's on the right-hand side of the distribution. Now, we need to figure out if we reject or not. So this is larger than this. So we place it right in there. And what that means is we're going to reject. Since the sample mean of 73 degrees is significantly more than 70 degrees, we must reject the null hypothesis. The room appears to be warmer than the stated temperature of 70 degrees. The thermostat may be broken. I say may. I usually try to keep a little bit fuzzy in there because technically we should be doing more testing. Okay, is this this is a two-tailed T. So it says the water bottle automatic filler machine is designed to automatically fill bottles to 60.5 ounces. Customers have complained. Sometimes the machine overfills the bottles and other times the bottles are not completely filled. So what I'm saying is it's sometimes high, sometimes low. To test the machine, you take a random sample of 15 bottle fillings, resulting in a sample mean of 62.5 ounces with a standard deviation of 7.5 ounces. Based on this research, is the machine out of tolerance? Perform a hypothesis test with a 5% level of significance. Okay, now this is a two-tail, and it's two-tail because of a couple things. I usually try to tell you right off the bat, sometimes high, sometimes low. The other term is sometimes they use the word different. Different just means not high, not low. Could be both. Write the information in. Okay, so our population standard deviation is unknown, and n is less than 30, and that's because we had 15 samples. Okay. So for our null hypothesis, it's going to be our null hypothesis in this case is the machine's doing what we thought it should be doing, which is 60.5. That's the stated figure. The other one is no, it's not. It's different than that. It could be high, it could be low. So in this case, we draw the picture. And because this is a not equal to, it's a two-tail. Okay. And when it's two-tail, what it does is it takes, now with the t distribution, we just use the two-tail step on our table. With the z distribution, we have to take that two-tail and the 5% and cut it down, divide it by 2. Like I said, with the t table, we just use the 5% for the two-tail. But we do have two tails, so that's important. Calculate the test statistic. So we calculate the test statistic 1.032. Okay, so we know that this one right here, these cutoffs are 2.144 and 2.144. So if this is larger than 2.144, then we're going to reject. But as you can see, and when we're doing these largers and smaller, technically the absolute value is the proper way to do this, because we're just looking at standard deviations away from the mean. So if this was so this is positive, and if technically if you said this was negative, this wouldn't jive. But we're actually we're just trying to measure standard deviations away from the mean, and so that's why the negatives don't matter as much, except they just tell us which side we're working on. So 1.032 would not be greater than either one of these. It would be like right here. Okay. So in this case, we say since the sample mean of 62.5 ounces is not significantly different than the population mean of 60.5, we must not reject the null hypothesis. The machine appears to be giving the right amount of water. The overfilling and underfilling people complain about may be inconsistent bottle capacity. That's a good idea. It's possible. Okay, this is a Z. I'm gonna try to find. Okay, this is a p-value. This is a Z distribution p-value calculation. So we've been using the rejection zone method for most of these. So this one is a P. Let me go back one more. Okay, that was rejection zone. So this is a p-value process. So this is the same question, but with a p-value. We've already went over this, so I'm going to show you how it's different. So this one, we're just going to try, this is Billy the Swimmer, and we're just trying to solve this with the p-value process. So it's just kind of for learning how this works. So for this one now, instead of having, I believe it was 1.65 right here, we're putting in 0.05. Some of you may think this is easier. So we're looking for a 5% level of significance. So we put in 5% right here. If it was two-tail, we'd put in half of that, and the other half would be over here. Okay, so we have 5%. We do the calculation, and we get negative 1.92. So now we're going to go to the z table because we need to get a p-value here to make this whole thing work. Okay, 1.92. One point 1.9 should be wait a second. Yeah, that's 0, so it should be this one. 1.92. So it's this one right here. Okay. 0.4726. So just remember 0.4726. Okay, so 0.4726. So we go over here, and this is where it can be a little bit tricky. So we have to figure out a little bit on where we're at with this whole thing. Now, one whole side is 0.5. And the way that this works is, remember that the z distribution always kind of starts in the middle and goes out. At least the alternative tables that I've been teaching from do that. So if this is 0.4726, this is a pretty big amount of the 0.5. So what we do is we take the 0.5 and we subtract the this should have a decimal point right there. Subtract the 0.4726, and it's going to be way out in the tail, and this is where this value will be. And so we end up with this p-value. The actual probability value is 0.02, or about 2.74%. So we're testing for 5%, and it ends up being about 2.74%. And that's how we figured that out if we're kind of doing it by hand. Your calculator, I believe your calculator will give you the p-score when you do this. So that's one way that we do it. The other thing in a prior, when we're talking about continuous probability distributions, we're talking about when we subtract and when we don't. So the reason why we subtract is because this calculation gives us everything but what we want, and that's indicative of we are looking for Billy swims faster, which means less, and we our inequalities point to the left. So in this case, we have to do subtraction to make this work. The other way you can do this problem would be you take this right here, you add it to the 0.5, which we kind of did in the older, continuous probability distribution ones. So you would take the 0.4726, add it to 0.5, and then subtract the whole thing from 1. And we get the same answer. We're just working with half of it. So in this case, it's the same scenario. We reject it, saying that he appears to be faster, but we reject it from our p-value calculation, which is, okay, we accepted that we could be wrong 5% of the time. And in this case, our calculation came up with 2.74. So what that means is our findings would occur normally 2.74% of the time, just by random chance. So if we're willing to accept the test that we would be wrong 5% of the time, we should be willing to accept that we are wrong 2.74% with this finding. So we reject the null hypothesis. Okay. Let's do another p-value one. Let's see. This is a z. Yes, this is a z. In this one, same scenario in this one. I probably won't cover this one too much. Same scenario in that we need to do subtraction to get this line out here, and that's just because our inequality, our alternative hypothesis inequality is pointing to the right, and I'm guessing we're looking for more than. So our math is going to get our values in the z table. It's going to give us everything but what we want. So in this case, we can take this and actually just subtract it from this side. It's the same thing, except in the continuous probability distributions, I would do 0.5 plus 0.4909, and then take that whole thing and subtract it from 1. In this case, we're just doing it from half of it. So yeah, this is I want to get to, okay, this is a t. Now this one is the thermostat problem, but we're solving it with the p distribution. So for this one, same scenario, we're thinking that the room is warmer than we thought. And so same setup, it is a t distribution problem, but with the p value. So in this case, now that here's the deal with these is that you cannot, if we go and we try to find the p value, use the p value rejection method, and we pull up the table, we can't do it. We have to use calculus to do this. So take a look at this. We go and we are trying to solve with 5%. So we say, oh, okay, great. 5%. What's the p-score for this one with the t distribution? And we go, okay, let's go take a look at the t table. The t table only gives us t-scores. It doesn't give us the area under the curve. And that's because there are so many different types of t distribution shapes that we have to use this thing called degrees of freedom, and the t table just gives us the t-scores. So we're stuck. We're stuck if we didn't have a calculator. So you have to actually use a calculator to get this value. Otherwise, you have to do calculus and to get the actual p-value for this. But here's the caveat. If you get the p-value for this and you calculate it, it's super simple. You get this small value and you go, oh, we're willing to accept being wrong 2.79% of the time. So we're going to reject it. The room is warmer than we thought. Look at all the math on this page, barely any. Super simple, but we can't do it by hand. Okay, this is a two-tail. So this is the water filling one, but we're using the p-score method of solving it. So let's see. We thought it was going to be 60.5. That's the standard. That's the way it should be. That's the stated amount. And then in this case, let's see, it is a t-score. So once again, we would have to use the calculator for this. And we would, obviously what we would do is, not obviously, but we would take the 0.05 and we'd split it by 2. And so we'd have 0.025 on each side. And so these are our edges that we now, when we do the calculated p-score, it has to be lower than 0.025. So, like I said before, we would have to use Excel or the calculator to do this because we're not doing calculus to get this answer. And we find out that it is right there. It is 0.3192, which is 31.92%. So this number this line would actually be a little more over here. So this is a huge, huge number. So that means we do not reject. The machine's doing fine. So these are examples on how this works with the P value process and the rejection zone value process. The big thing is you have to work these things out. I do have more videos on how this works with the calculator, and I highly recommend you take a look at that. It is, as I mentioned before, yeah, you cannot do the p-value process without the calculator. Other than that, the rejection zone method works really well. It's an older method, but you can solve the you can reach a conclusion just as easy as you normally would be able to. Okay, thank you.